Okay, started the live stream.
Hi, everyone. Welcome to the Astronomy Colloquium. Today's speaker is Dr. Ilaria Caiazzo. She's a Sherman Fairchild Fellow in the Walter Berg Institute for Theoretical Physics at Caltech, which is also otherwise known as TAPIR. Ilaria grew up in Italy, attending the undergrad physics program at the University of Pisa, which is widely regarded as, the best undergrad program in physics in Italy.
I actually did it in Genova, but I did a brief time in Pisa as well.
And then a master's degree at University of Milan. She obtained her PhD at UBC, working with Jeremy Heil, who's a well-known expert in theory of magnetized, and who himself was a Fairchild Fellow at Caltech some 2 decades ago. Ilaria's interests are broad, but they're roughly centered on what I would say degenerate objects, brown dwarfs, white dwarfs, and neutron stars, especially magnetized. For her thesis, she studied the initial mass to final mass relation for white dwarfs using Hubble, Gaia, and other facilities, revisited the fate of old brown dwarfs in globular clusters. Separately, and not surprisingly, in collaboration with her advisor, she carried out a major theoretical program in polarization as a probe of exotic QED effects, which you expect to see in magnetized, and it's that, as it turns out, by extension in the work she had done, also in the accretion disks of black holes, where the magnetic fields can be quite large too. We this year on finally verge of finally seeing these effects. IXPE is expected to be launched in December of this year. Ilaria is a member of both XP, as it's called, and the Chinese EXTP mission, which has got similar goals but larger, and launch date is 2027. Ilaria showed a lot of leadership as a grad student. In response to a call from the Canadian Space Agency for a new mission, she organized all the high energy theorists and appropriate experimentalists and proposed a mission called Colibri, which is like the hummingbird in Italian, whose motto is taking the pulse of neutron stars and black holes via microsecond X-ray spectral timing observations. This would be like nicer, except with TES detectors. So let me end with a couple of stories. I think it was like late fall of 2018, if my memory serves me right. Jeremy, with whom I'd worked when he was a postdoc here, called me up and was, and here Ilaria may start blushing, was full of praise for Ilaria. It was clear to me that given her wide interest, should be an excellent candidate for a Berg Fellowship, and was very happy to learn that my colleagues upstairs made the right choice and she did win a fellowship. But she's, of course, an honorary member of the ZTF Stellar group in addition. Ilaria's interests actually go even beyond this. Along with her husband, she's a movie producer. And if you go to her website, ilariacaiazzo.com, you can see a clip of a movie they're making called The Recycling Man. It's a very high production thing. And soon I think it'll go into a series. I don't know the details. So Ilaria is a really good-spirited person. I was trying to come up with some jokes. It's a nice thing to always end jokes, makes the speaker feel uncomfortable, but really I couldn't. What I could say is that recently she got the vaccine like anyone else, and I think it was the second one. And she got the vaccine, first one, second one. And then she wanted to give me a bottle of Barolo, I think, because she had returned from Italy. So I told Ilaria, look, after you get the vaccine, I was just joking. I didn't tell her that way, but I told her after you get the vaccine, why don't you come by, we'll polish off the Barolo, and next day anyway, you'll be feeling terrible. So you might as well combine it with the hangover. And she took that in good spirit, and that's how that day ended. So welcome again, Ilaria. Looking forward to hearing some new stuff that we've been doing in the last year.
Thank you very much. And actually, the next day I felt very, very bad. Indeed. Thank you, Shri, for this great introduction. And thank you very much to the committee members for giving me this opportunity to present my research. I've been at Caltech for more than a year now, and I haven't had the chance to meet that many people for obvious reasons. So I'm very happy to have this chance to tell you guys about my research. And I'm going to talk about different works that I've been doing all about white dwarfs, and part of them with my collaborators at the University of British Columbia, and part of them with my collaborators here at Caltech. And I'd really like to convince you that this is an amazing time to study white dwarfs. But let's start from the obvious. As you all know, white dwarfs are the most common star corpses. All stars with masses below 7, 8, 9, we don't know, but about that, solar masses, they become white dwarf at the end of their lives. So that means that more than 90% of stars, about 95% of stars, are destined to become white dwarfs at some time, at some point, right? And so white dwarfs are very common, and they're very well-studied object. If you want to make a comparison to other star corpses, neutron stars, so here is just an example. We're looking here on the left at the cooling curve of a theoretical cooling curve for neutron stars. And these are all the neutron stars known that have thermal emissions from the surface, through which we can get a temperature. They used to be called the Magnificent Seven. They're a little bit more than 7 now, and if you throw in Crab and Gemingen and Vela, they're even more. But not much more than a dozen. While here on the right, you can see the same things for white dwarfs, the cooling curve, like that, how they dim with time. But the white dwarfs in this picture are just the white dwarfs in one Hubble field of the globular cluster 47 Tucani, and there's thousands of them. And they're all at the same distance, all the same metallicity, all about the same mass. And the difference between them is just the age. So it's like seeing different snapshot of a single white dwarf cooling with time. And I'm going to talk more about why star clusters are amazing to study white dwarfs. But you can see the stark difference here. And for this reason, white dwarfs are very well studied, and we have very sophisticated and wonderful theoretical models that describe the physics of white dwarfs, how they evolve and how they cool. And so you might think, we know everything about white dwarfs. And for the typical white dwarf, that's pretty close. We know a lot. And so this is kind of like the white dwarf that you think about, especially if you don't work on white dwarfs, about half, 0.6 the mass of the sun, and a radius similar to that of the Earth, a core of degenerate carbon and oxygen mixture, and then a thin layered atmosphere of helium and hydrogen. And here you can see the spectrum of the typical white dwarf. You have a blue continuum, and then absorption line of hydrogen, the Balmer series. Quite broad, because the gravity is quite high on the surface of the white dwarf. So this is the typical white dwarf, and we know a lot about it. However, there's still a lot of interesting mysteries and open questions about white dwarf, and those are mostly connected to the atypical ones. For example, 0.6 solar mass white dwarf, we know what it's made of, we know everything about it. But as soon as you go to higher mass, most models predict that above 1.1 solar masses, a white dwarf should be made of mostly oxygen, neon, sodium, and magnesium in its core, because the progenitors are expected to ignite carbon. However, we are not sure. We are not sure what these white dwarfs are made of. There's actually some indication, some observational indication that some, at least very massive white dwarf, might still contain carbon and oxygen. So this is still a big mystery. Another big question about massive white dwarfs is what type of star creates what type of white dwarf. So what's the relation between the initial mass of the progenitor star and the final mass of the white dwarf? And there are a lot of implications to stellar evolution hidden in this question. For example, what roles do winds have at the end of the star life in determining the mass of the white dwarf at the end? What type of convective overshoot goes on the horizontal branch of the progenitor stars and things like these. And if the initial mass final mass relation is quite well known for lower mass white dwarf and lower mass progenitor, as you go closer to the maximum mass for the progenitor, maximum mass of the white dwarf, we have very few objects over there to determine this relation. And a connected question that is also extremely interesting, even more interesting maybe, is what is the maximum mass for a white dwarf? And we still don't know. For what is the maximum mass for which a star produces a white dwarf instead of becoming a neutron star? And that also is full of implications for other fields. For example, what is the rate of core collapse supernovae? What's the number of neutron stars that we should expect in the galaxies? And things like that. And I will not go through all of the open questions about white dwarfs because we might need the entire afternoon, but I just also wanted to show you that white dwarfs don't come only in one flavor of atmosphere. They come in very different flavors, and to each flavor, there are puzzles attached to it. For example, here again, we see the spectrum of a Da hydrogen-dominated white dwarf with its beautiful Barmer lines. But there are white dwarfs that have atmosphere that have only helium in them. You can see here a DB and a DO. And you have helium-1 and helium-2 lines over there. And we still don't know what makes the hydrogen goes away. It could be that it gets all depleted through a late nuclear burning phase that only happens to some white dwarf, or it could be something related to more like the evolution of the white dwarf itself. And then there's others. There's carbon-dominated atmospheres, the DQ. Here we have even, and then there's the whole field of polluted white dwarfs. Some white dwarfs show metal lines in their atmospheres. And, the gravity on white dwarf is extremely strong, so metal sinks very fast. And so if you see metals in the atmosphere of a white dwarf, that means that it's been constantly polluted by something. And so there's this huge field of people just thinking, what might be polluting these white dwarfs? It could be planetary debris, it could be comets, it could be asteroids. So it's like, again, each of these different atmospheric composition comes with their own puzzles. And then my favorite types of atypical white dwarfs, magnetic white dwarfs. About 20% of them, of white dwarfs, are observed to be magnetic. And not only that, the magnetic fields span a huge range, about 5 orders of magnitudes, between a few tens of kilogauss to almost 1 billion Gauss. So, and we don't know what's causing only some white dwarfs to be magnetic and what's causing this huge difference in fields. And there are a few explanations that has come out in the years. Of course, the most obvious one would be they come from magnetic progenitors, right? There's some stars called BP stars that show magnetic fields much stronger than other stars, about a few tens of kilogauss. But the problem is that they're just not enough. They're way too smaller percentage to explain 20% of white dwarfs. So there's other explanation proposed that can be divided into kind of big groups. One is like from evolution and the other one is from interactions. And here I'm just listing another 2 from the evolution side, one of which Jim has proposed with other collaborators, which is that they have been finding indication that some magnetic fields hide some stars hide magnetic fields in their convective cores. And so those could be the progenitor of magnetic white dwarfs. Another recent explanation has been proposed to be that when white dwarfs cool and freeze, the white dwarf crystallization, the phase separation during white dwarf crystallization creates some dynamos that create some magnetic field. So this particular one, though, can only explain quite weak magnetic fields. And then there's all the other group of models that involve interactions. For example, both accretions in binary interactions and mergers of two white dwarfs. During those processes, you expect strong dynamo to arise and to create very strong magnetic fields. So I'm going to stop here talking about all the open questions, and I haven't even started talking about all the ones regarding white dwarfs in binaries. These are just about single white dwarf, but I could spend the whole afternoon again, so let's move on. But I hope I convinced you there's still a lot of open and exciting questions about white dwarfs. And now what I want to convince you next is that this is a great moment to study white dwarf. And one of the reasons is, of course, because of Gaia. So Gaia, which is with this amazing database of parallaxes and proper motions for billions of stars all over the sky. It's been really transformational for a lot of fields in astronomy and astrophysics. And of course, white dwarfs is one of them. Because, you know, how do you find a white dwarf? Before Gaia, using only photometry, it was hard because, of course, white dwarfs are blue objects. But in order to distinguish them from, you know, high-mass stars or quasars or other blue objects, you have to know the distance. And for example, if the white dwarf is in a cluster, then you know the distance from the cluster, and then you can see, oh, that's a white dwarf. But otherwise, you're out of luck, and you need a spectrum to be able to be sure that that's actually a white dwarf. And before Gaia, in fact, most of the white dwarfs known were identified through the Sloan spectroscopic survey. After Gaia, now we have parallaxes for many of them. And so we have not only the color, but the absolute magnitude. And here I'm showing the Gaia CMD, and here they are. The white dwarf are just this bunch of objects in the lower left corner. Of course, there's more study that goes into here. You know, for example, Gentile Fusillo and his collaborators have been working a lot of creating a pure sample of white dwarfs, not just by making a rough cut here, but that's the principle, finding white dwarfs through the color and absolute magnitudes. And so you can see how transformational that was. Here before Gaia, this was the known white dwarfs, about 30,000 white dwarfs, mostly concentrated in the northern hemisphere because of SDSS, and a very biased, a very not uniform sample. And then this is white dwarfs of the Gaia DR2 catalog. And so much, about 300,000 white dwarfs, a much more uniform, deeper sample. So this is from the catalog of Gentile Fusillo et al. Of 2019. And they are working now on EDR3 that came out late last year. And they are thinking about, you're going to go better parallax, more uniform, deeper. So it's going to be about 400,000 white dwarfs. So you can see that here, the numbers of white dwarfs have increased tenfold thanks to Gaia. And not only, the sample now is way less biased and way more uniform, and you can study them as a population. And there's been a lot of papers that you can check out. There's been a lot of research thanks to Gaia on white dwarfs as a population. But if this wasn't enough, if you pair Gaia with spectroscopic surveys like ZTF and TESS, etc., then you can go look for the strange white dwarfs, the ones that for some reason show photometric variation. And Of course, I work with ZTF that you all know, Zwicky Transient Facility, that has been run here at Caltech by Sri and Matthew and Eric Belm at University of Washington. And again, I can spend the whole afternoon just telling you how amazing ZTF has been with transient and how an exciting time now it is for time domain astronomy. But this introduction is going very long, so I'm going to skip that, and I'm just going to tell you how an amazing facility ZTF is also for variable stars. And that's because ZTF has a huge field of view, 47 square degrees, and at each pointing, it records the photometry of all the objects in this huge field of view. And so it has very high cadence, and you can accumulate hundreds of epochs of each object. And this is amazing to find variable stars, and in particular, periodically variable stars. And I work in the team of variable stars at ZTF, and they have developed a great pipeline. Shemek Rose has just recently developed a new pipeline for the photometry, and Kevin Burge has developed this very fast period searching to looking for periodic variables down to very low periods of just a few minutes. That goes very, very fast. So I've been very lucky to working with them. And in particular for white dwarfs, the variables that you can find comes in many flavors. Of course, you have the pulsators, which also come in very many flavors. Is the SETI, the hydrogen-dominated ones, the helium-dominated atmospheric pulsating white dwarfs and STP pulsators. And then you have the magnetic rotating white dwarfs, which I'm going to spend a big deal of time talking about just in a bit. And then there's all of the accreting and detached binaries that the variable group has been working a lot on. Here I have the picture from Kevin's paper on eclipsing double white dwarfs, and then there's AMCVNs, white dwarf, brown dwarf binaries, and this is all the work that Jan has been working on. So I really invite you to go and check their papers. But yeah, ZTF is great to find weird white dwarfs that are interesting because they show some sort of signs of variability. But then now I think it's time to get to my research, and I'll go in order. I'll start from things that you can do just with Gaia, and then I'll move on to things that you can do with Gaia and ZTF. And I'll start with my work on white dwarfs in open clusters. I already mentioned before how amazing clusters are for studying white dwarfs and in general for stellar evolution. They are these groups of stars that are all at the same distance from Earth, all born about the same time, and all with the same metallicity. So they're really great for studying stellar evolution. And in terms of white dwarfs, they're great because you can get the age of the cluster itself by fitting an isochrone on the main sequence. And then you can get the age of the white dwarf by its position in the CMD and by the spectrum, the cooling age, I mean. And so you have the total age of the white dwarf. And then you can know what is the initial mass of that white dwarf, what kind of stars produce that white dwarf. And that is exactly how this figure that I showed you before has been put together. This is Jeff Cummings and collaborators 2018. They just looked at open clusters, so young open clusters, to look for massive white dwarfs and create an initial final mass relation. However, this was pre-Gaia. So the only way you could figure out that a white dwarf was in a cluster is just because it's in the vicinity of the cluster, it's in front of the cluster, and it kind of makes sense for it to be a member, right? And that means that many of these stars could just happen to be around the cluster, but not being cluster member. So with Gaia, though, it's much easier to get a clean and high confidence cluster membership. That's because Gaia provides proper motion and parallaxes for stars all over the sky. And so you can just take your cluster, cut a region of the sky around that cluster, and find all the stars that have the right parallax, so they are at the distance of the cluster. And on top of that, you can select the stars that are moving with the cluster. And they're not just by chance at the same distance of the cluster and maybe just passing through. And so, because if the stars were born with the cluster, they must be moving with the cluster. And that you can do by doing a cut in proper motions. And so you get an extremely clean sample of high probability cluster members. And once you do that, then you make the CMD. And here, for example, I have the CMD of 3 clusters. Don't remember which ones, but you can see 2 of them happen to have a white dwarf down here in the left corner. And so what you do is you go and get a spectrum of the white dwarf, and from the shape of the spectrum, and in particular from the shape of the absorption lines, you can determine the mass and temperature, and therefore cooling age of the white dwarf. And then from isochrone fitting, you get the age of the cluster. And then you can also have the initial mass of the star in that way. And so that's what we did. We researched with my collaborator at UBC, we searched for white dwarfs in about 300 young clusters with ages less than 500 million years to find new white dwarfs, new massive white dwarfs, and to check all the white dwarfs that were considered cluster members to make sure that they were really cluster members. And so this is the new initial final mass relation that we got from that work. It only starts at 2.5 solar masses. We only looked at young clusters. And so you can see that we find a few new white dwarfs here in red, and that many of the white dwarfs that were in the previous plot that I showed, not many, but a few of the white dwarfs that were in the plot that I previously showed, were either too faint to be in Gaia and to have a decent parallax measurement, or they happened to actually not be cluster members. So we had to remove a few white dwarfs that just happened to be in the right place at the right time. So just a few takeaways from this new plot and this new initial final mass relation. First of all, there could seem to be a little bit of a break in the slope around 4 solar masses, but it's very much a hint. So it's like the error bars are just too big for now to see this as a real break, but it's interesting. And I'll talk a bit more about this later on. Another interesting thing that I will talk more later is that 3 of these new white dwarfs happen to be magnetic. But just like now focus for a second about just the sheer number of white dwarfs and what the type of white dwarfs that we found. First of all, we were expecting to find more white dwarfs. Even if you consider that many are hidden in binaries, you still found way too little white dwarfs for the amount of clusters that we surveyed. And this is interesting, but it might be somewhat expected, because even if the white dwarfs receive even a tiny little kick at birth, in a few million years, then the white dwarf is out of the cluster. So it's not surprising that we didn't find as many as we expected. And the other 2 things that you can see from the plot is that we didn't find any white dwarf with masses above 1.1 solar masses. And the maximum mass is supposedly 1.37 or something. So there's a lot of space there to find more massive white dwarf, but we didn't find any. And we did not find any white dwarf with a progenitor mass above 6.5 solar masses. Now, neither of these means that, the maximum mass is 6.5 solar masses, or that clusters do not produce very massive white dwarfs. It might just mean that the more massive white dwarfs are the first one to be produced by the clusters, and so they get kicked out more easily and they have more time to get out of the cluster. So we might have just not been finding them because they might have gotten out. And so this is very preliminary, but just to show you what's the next step in finding these escapers, we are now working on finding the escapers from the clusters. And not only white dwarfs, all stars that are escaped, because clusters kick out stars all the time. And so we are now looking for the escapers. And this in particular is the Pleiades. This purple blob here is the Pleiades, and these yellow stars that you probably cannot see here is the sun. And so we are surveying this like huge chunk of sky. This is the center of the galaxy. So we're looking 100 parsecs towards the center of the galaxies and 200 parsecs toward the outskirts where the Pleiades is. And so looking for escapers. And here, all of these dots, they're divided in kind of chunk of ages of them that have been escaped. Like the red one escaped less than 25 million years ago. The green ones escaped less than 50 million years ago, etc. And so we are just selecting all of these objects that just by their kinematic, sometimes in the past, they were very close to the Pleiades. And so again, this is the Pleiades again, and these are all the CMDs that we are of the escaped star. And first of all, it's quite remarkable how similar this, I haven't put in a CMD of the Pleiades, but if you look at this guy over here, that's exactly how the CMD of the normal Pleiades look like. So it's quite amazing that these CMDs that we're putting together of the escapers look really much like the CMD of the Pleiades. So that, of course, there are a few interlopers, like this guy over here. It's probably not a Pleiades member. It's just some star that happened to have the right kinematic. But all the others, they seem to be Pleiades members escaped in the past. The other interesting thing is that if you look a long time ago, you see that most of the escapers were low mass stars. And that makes sense because the low mass stars are the easier to be kicked out from the cluster. And while if you go closer to today, you see also some higher mass stars. So this is all very exciting. And so we are putting together all of these escapers and we're finding a few white dwarfs. So for the Pleiades, we actually found 2 white dwarfs that make sense to be. So one white dwarf is already in the center of the cluster and we found 2 additional ones that are escapers. And the other cluster that we looked at for now is Alpha Per, and we found a white dwarf escaper also over there. So you can see one of the Pleiades one was already there. I don't know if it's this one or this one. And the other 2 are 2 new ones. And there's Alpha Per over here. So this is the new initial final mass relation with the escapers in it. And you can see that these 2 new ones are the most massive that we have. And they are really pushing to have this kink in the slope over here. Of course, it's still okay. Like one slope is still kind of okay, but it's really pushing it now. And you can see if you just extrapolate to the maximum mass for a white dwarf, a little bit below 1.4, you can see that depending on which slope you take, the progenitor for the maximum mass white dwarf, then it varies quite a lot. Again, this is all preliminary, but I just wanted to show what we're going to do now to find all the escapers. And another interesting thing that I'm showing here is that remember I showed you how I told you that the Pleiades CMD looks very much, the escapers look very much like the Pleiades CMDs. So you can just look at the dispersion, how the deviation from what you expect from the Pleiades CMD or from the Alpha Per se CMD. And you can see that it stays pretty low until all of a sudden the CMD doesn't look like the Pleiades at all. And similar for alpha per here, there's very little deviation from what you expect. And all of a sudden, the CMD just doesn't look like the cluster at all. And if you look at the age for that to happen, that is extremely close to the age of the clusters themselves. The Pleiades have a quite uncertain age, around 120, 150 million years, and Alpha Per has an age of about 80 million years. And this could be an actual new method to figure out the age of these clusters, especially because for some clusters, it's very hard to figure it out just from the main sequence because they don't have any evolved stars. But again, this is all very preliminary and all very exciting. The paper is going to come out soon. So I just want to go back now for a second to the initial final mass relation again, and to this point over here. The fact that 3 of the white dwarfs that we found turned out to be magnetic. And why is that interesting? So you remember that a few minutes ago, I was talking about magnetic white dwarfs, and now there are all of these possibilities for the origin of magnetic fields in white dwarfs. And having this white dwarf is actually here, ACC 47, M39, and M47. These are the 3 white dwarfs. These 2 are about 1 megagauss. This guy is about 2.5 megagauss. And having them in these clusters, tells us a lot about their origin. First of all, they're hot and young. Here, this guy here is the hottest white dwarf found in a cluster. It's about 100,000 Kelvin. So for sure, the fields cannot be produced by phase separation during crystallizations. These guys are not crystallized. The other thing is that the clusters are way too young to have formed 2 white dwarfs that could merge and not explode in a type 1a supernova. The clusters that these white dwarfs that these clusters are forming are around 1.1 solar masses. And if you merge those 2, you don't get the 1.1 solar mass white dwarf. So that's also out of the way. There is no indication of a companion whatsoever. M47 has a little bit of an infrared excess, which is, I don't think, though it can be explained in any way by a companion, it just doesn't fit. It might be more like a debris disk. It's something that we're still trying to figure out. But the other 2 do not have any indication whatsoever of a companion. And so accretion is kind of out of the way as well, because where would the companion be? And also the cluster have a very, very small binary fraction. If you look at here, there are the 3 clusters. I don't know if you look at the blue one, ACC 47, you can see that there is no binary sequence over there almost at all. The only cluster that has a little bit of a binary sequence is M47 here in green. You can see a few binaries over there, but very, very little. So that also kind of, there could have been still mergers on the main sequence that created these magnetic white dwarfs. But I still find that a little bit unlikely. The strike here is a little bit thinner because it's kind of unlikely, but still possible. And also, we found 3 out of 5 white dwarfs to be magnetic. So the magnetic ABP progenitors are not a good explanation because there's just not enough of them. It's just too high fraction. And so, for this particular white dwarfs, the most likely explanation is that they were born with these fields, and that something in the progenitor stars created those magnetic fields. And you can see the only explanation that is not ruled out is that the magnetic field might be hidden in the progenitor stars, like in Jim's work and Matteo Cantiello and so on. But so this is for this particular one. So there are proof that at least for some white dwarfs, they are born magnetic. This doesn't rule out the other possibilities for other white dwarfs. And in particular, the mergers of two white dwarfs, we expect the dynamos that arise in the mergers to be very strong. And so we do expect that the merger of two white dwarfs would create a highly magnetized white dwarf. So all of these processes might be going on at the same time and create different types of magnetic field. And that's maybe why we see such a big range of magnetic fields, right? With just different processes at work. And to study this different process, the merger of two white dwarfs, I'm going to now move to the other part of my talk, which is looking for merger remnants. Are there any questions? I'm going too fast, probably. Whatever. Next part, how do you find a merger remnant? So I already covered the highly magnetized part, but there's other characteristic that, you pick up a white dwarf and you can say, oh yes, that's a merger remnant. And one is that, remnants are more massive on average than no mergers. Of course, you can find two very low mass white dwarfs that merge and create an average white dwarf. Kevin is finding lots of these extremely low mass binaries white dwarfs. But on average, the average white dwarf is about 0.6 solar masses. So you expect that on average, the merger remnants will be above 1 solar mass. And the other characteristic that is really a smoking gun for merger is rapidly rotating. So white dwarfs rotation period are quite slow. There goes from hours to days to years, but I think the most normal period is about days. While for mergers, you expect them to be rapidly rotating because you have all that angular momentum coming from the binary angular momentum, from the conservation of the binary orbital angular momentum. And so since highly magnetized white dwarf are expected to have a non-homogeneous emissions on the surface, and if they're rapidly rotating, they can be photometrically variable. And so you search for them with ZTF. So what kind of periods are we looking for? Well, that's tricky. There hasn't been that many studies on the merging of two white dwarfs. But here there's been this great paper that came out this year from Josiah Schwab that studied the evolution of the remnant after the merger. And so you can see here in this cartoon that, right after the merger, the remnant is spinning very fast, a sub-minutes period, because of all the angular momentum of the binary. But the merger doesn't stay compact. It puffs up almost immediately, about a year or 1,000 years, to a giant phase because of all the shell burning. And now the object is about tens of solar radii. And so it's so big that it's rotating way above its breakup speed. And so it's you have here a lot of winds and a lot of angular momentum is lost through winds. So when the white dwarf goes back, so when the remnant then starts contracting and become a white dwarf again, the periods that you expect are more of the order of 10 to 20 minutes, as you see here, right? So it's not sub-minutes periods, but it's something around 10 to 20 minutes. So that is exactly what we looked for. Here is the Gaia CMD again. And so we looked down here below the white dwarf track. So this is the main white dwarf track. White dwarfs along here are about 0.6 solar masses. And if you go down, this is where the more massive white dwarfs resides. And so that's where we looked for very massive white dwarfs. And we looked for periods of about a few minutes to a few hours. And here is an example of a ZTF light curve for one of the objects that we found. This is a particularly interesting and pretty one, multi-peaked, but most of them are just sinusoidal light curves. So we have all of these interesting sample of about 30 objects, and they all showed this quite big variability. Like here is like a few tenths of % variability. And so to understand what they are, we needed follow-up spectroscopy. But before we go into the follow-up spectroscopy, let me just tell you what to expect when you're looking for magnetic white dwarfs in terms of spectra.
Ilaria, you've got about 10 minutes left.
Oh my gosh, okay. I'm gonna be quick. Thank you. So if you have magnetic field, what happens is that the magnetic lines, so the absorption lines here, like the hydrogen absorption lines, instead of having just one, H alpha, you have three. They get splitted. You have Zeeman splitting, and it's just the three different magnetic quantum numbers of the electron levels. And here it goes. Here is a 2 megagauss, 11 megagauss, 30 megagauss. So the higher the magnetic field, the bigger the separation between the components. And here you're seeing the same thing, right? This is the wavelength of the transition. This is H alpha, H beta, and H gamma. And as you go higher with magnetic field, you see that you have, at the beginning, you have this splitting tree that becomes bigger and bigger. And then all of a sudden, you have more components, and they shift in energy and wavelength very quickly. And this is the reason why sometimes magnetic white dwarfs just look featureless, because if you look at certain regions, the wavelength is changing so quickly with the field that if you have a certain distribution of fields on the surface of the white dwarf, you don't expect just one strength, but I don't know, a dipole or even a more complicated structure, then the features get completely washed out, and you end up with featureless objects. But there are some region of the magnetic fields, where these lines kind of go to a minimum or a maximum in wavelength. These are called stationary features, and the features stay stable for big range of fields. And those are the features that you look for to identify the magnetic field. And here you are. So this is some examples of the objects that we found. This one, for example, you can see the stationary features are down here. This is about 175 megagauss, 19 periods rotation. This is a particularly pretty one because, you can see all of these very sharp features. So this one is very strange because the field is very uniform on the surface. This is definitely non-dipolar. This is something way more uniform because you can see the features are extremely sharp. And this is about 105 megagauss. It's another 20 minutes and 250 megagauss. So we're finding a lot of them to be extremely high magnetized. And those were hydrogen ones. We even have DQ, so carbon-dominated magnetic white dwarfs. You see one here. Helium-dominated magnetic white dwarfs, one here. And then we even have some very strange features that are super interesting because they might be cyclotron feature. You can see this extremely broad and shallow features. This might be the first indication on a white dwarf that there is cyclotron absorption. So each and every one of these objects is extremely interesting per se, and you're still collecting them and analyzing them and characterizing them. And we are now modeling them with magnetic white dwarf models. But we found, as you can see here, the stars are the ones that we followed up and turned out to be magnetic. And almost all of them turn out to be magnetic. So this is an extremely interesting sample because they're all very massive, magnetic, and rapidly rotating. So this is a sample of bona fide white dwarf mergers. And so you can imagine that you can see the potential here, right? Like you can get them together and you can understand a lot of questions about merger remnants, like what's their composition, how do they evolve, what's the delay time between the formation of the binary and the merger of the two white dwarfs, and all of these questions. And then you can calculate the merger rate in the galaxy. What's the merger rate of white dwarfs right below the Chandrasekhar mass? And that can tell you what's the rate above the Chandrasekhar mass, and compare that with the type 1a supernova rate and see, is it too much? Is it not enough to explain the type 1a supernova rate? And then last but not least, it's understanding magnetic field in white dwarfs. This is an amazing new sample of extremely highly magnetized and hot white dwarfs, which is, we had about a few before, and now we have 30 and counting. So this is a great new sample, and we're still working and characterizing them. So this is, again, very preliminary, but I hope you see the huge potential here. And since I have like 5 minutes, I'm just gonna conclude with the part that is the title of my talk, the tiniest white dwarf. So one of the white dwarfs that we found, ZTF 1901, it's like actually one of the very first. You can see here is the bluest, one of the bluest objects in Gaia. This is an image from Pan-STARRS. It's like one of the most extreme in our samples. Its period is only 7 minutes, so one of the shortest period for a rotating white dwarf. And this is the spectrum. The magnetic field is 800 megagauss, one of the highest, the highest in our sample and one of the highest ever detected on a white dwarf. And we got some swift UV photometry to characterize the temperature and radius of the white dwarf. And since the parallax is so good, the measurement of the parallax is so good, this object is only 40 parsecs away, we could have very strong constraints on the radius of the white dwarf. And so we found that the radius of this white dwarf is only 1800 kilometers. And, as I told you at the beginning, the typical white dwarf has the radius of the Earth about, or even a bit bigger. Our white dwarf is the radius of the Moon. It's very, very tiny. So this is the second smallest white dwarf known, which is also extremely magnetized and rotating very fast, by the way. And so the small radius means a very large mass. As you know, the smaller the white dwarf, the larger the mass. And depending on the internal composition that you assume, it's about 1.35, 1.37 solar masses. So this is the more massive white dwarfs ever found, the closest to the Chandrasekhar limit. And not only that, being so massive and being so small, this white dwarf is the first one found that is cooling through Urca processes. So through neutrino emission due to electron capture. So in the interior of the white dwarf, it's so dense that it's above the threshold for electron capturing on sodium. So the nuclei of sodium are capturing electrons and becoming neon. And so this process, the neutrino emitted in this process are the ones that are driving the cooling of the white dwarf, similar to what happens in neutron stars. And so this is already quite amazing. And as right now the white dwarf is completely mixed. So there's sodium all over, but the sodium keeps sedimenting because of the high gravity of the white dwarf. And so this process is still going on right now. Sodium goes into the core and captures electrons. And the more electrons it captures, the less electrons are there to provide support. Because of course, the electrons are the one providing the electron degeneracy pressure. And so if this continues, the white dwarf will keep shrinking. So right now it's, here is the mass radius relation for different compositions. This red line is the oxygen neon composition that we expect for such a massive white dwarf. And this solid red line is if you include electron captures. And you can see here we are above the density for electron capture on sodium. And we're very close to the density for electron capture on magnesium. And so if If the star keeps shrinking until it hits this electron capture zone magnesium threshold, then it will keep collapsing and it might be unstable. So this is very speculative. What may happen is actually that the white dwarf will freeze way before that, because these Urca processes, this neutrino emission is extremely good at cooling the core of the white dwarf. So it might actually freeze very fast. So this might not happen at all, but it's still an interesting, concept, because if the star collapses, depending on the dynamics of oxygen burning, it might either explode in a supernova or collapse into a neutron star. So this type of white dwarfs could be progenitors of neutron stars. And for example, of course, it's very, again, this is very speculative. It might not happen at all. We need to put more study in it. And like actually Josiah just is going to publish a paper soon where he ran a lot of MESA models. And it seems that this white dwarf is going to freeze way before that. But in case this happens, in case this white dwarf might be progenitors of neutron stars, there would also be very common progenitors, because this object is only 40 parsecs away and it's very young. So if we find it that close and that young, it means there's a lot more out there. Okay, I leave it here because I'm out of time. Thank you very much for your attention.
All right, thank you, Ilaria. I wish we could give you a big round of applause. Instead, you're going to have to settle for a little bit of silence and hopefully a few questions here. So, okay, Catherine, go ahead.
Where you showed the smallest white dwarf on a color magnitude diagram, it was at the end of a sort of stripe of extra density. And I just wondered what that feature sort of sticking out from the main white dwarf region was.
Ah, that's a very good question. You mean here?
Yeah, there.
Yeah, and actually this is a bad CMD. The white dwarf is actually a bit higher than this streak. This is something that was found thanks to Gaia. It's called the Q branch. It's an accumulation of white dwarfs, and there's still a lot of debates of what those white dwarfs are. I actually showed this quite early again in the talk, if I can go back very quickly. These plots that I saw at the very, very beginning. Almost there. There you go. Yeah, okay. You can see here, this is from a paper from Evan Bauer et al. And you can see here they're showing this overaccumulation. And it seems that this overaccumulation falls where the CO crystallization is expected to happen. So that's the indication that I was telling at the very beginning, that some of these white dwarfs might be carbon-oxygen, because the oxygen neon crystallization is expected in models to happen a bit higher up, a bit brighter. And so this could be carbon-oxygen white dwarf crystallizing, but there's a lot of debate on what this Q branch looks like. There's also the thing that a lot of these stars happen to have very, very high proper motions. So they might be, you know, mergers or kicked out stars, or who knows. But good eye.
Thank you.
Okay. Okay, next question was from Sterl.
Yes, so in the evaporation of your clusters, there are 4 ways that clusters evaporate. There's sort of relaxation evaporation, which can be enhanced by early mass loss that expands the cluster beyond the tidal radius. There are binary interactions that people have talked about for 40 years. There are birth kicks of white dwarfs, such as we see evidence for in globular clusters. Can the relaxation in binary stars would preferentially eject lower mass stars, but you mentioned that the CMDs looked identical to the ones that were remaining, I guess. Is that surprising? And from the ratio of the white dwarfs to the other ones, can you say anything about the birth kicks of white dwarfs?
So I think that from the fact that we don't find the more massive white dwarfs at all, and we found so very few white dwarfs. This is a really big hint that white dwarfs get some sort of kicks, because the progenitors were the most massive stars in the cluster, and yet we are not finding the white dwarfs. Of course, the relaxation times are very small, so it's very easy to kick them out. But if you go to the reconstructing the clusters, if you see here the first one that were kicked out, this one is 100 million years ago, 75 to 100 million years ago, they were all low mass stars. So if you go to more recent, you can find some higher mass stars. But at the very beginning, the first one to be kicked out were the low mass stars. So this kind of makes sense for what you expect. It's much easier to kick out the low mass stars, and then if you go closer and closer. But yeah, if you go to the 0 to 25 million years ago, this CMD looks strikingly like the CMD of the Pleiades. Very, very, very similar. Down, and the biggest hint is like these pre-main sequence stars, right? This look very like in the Pleiades. While if you just take a random part of the sky, you see that most of the stars are actually on the main sequence. So did I answer your question? Like this one, the one that is the most recently kicked out are kind of like a snapshot of the same CMB as the Pleiades. But if you go further and further away and further in the past, the first one to be kicked out were the low mass. So it took longer to kick out the bigger mass, the higher mass stars.
Yeah. So certainly it would be interesting to think about that, in light of all the ideas. I mean, there are lots of people who've done dynamical modeling with different binary fractions and different tidal radii and things, and maybe one could try to back out some constrain some of those, and see how much extra you need for the white dwarfs, if anything, and so on. So,
yeah, that's the plan. Like, as I said, we just started working on this, but yeah, that's the plan. Now that we have this method to find the escapers, now we can start constraining all of those models for how they get kicked out and what's special about the white dwarfs, right? I think for the white dwarfs per se, just finding so few, that's a big hint that they get kicked out. They have kicks on top of just being normally evaporated. But again, we have to put more solid constraint on that and compare them to the models. That's the next step.
Okay, we're running over time, so I'm going to give the last question to Wenbin. Dave, if you want to stick around for the faculty meet and greet, you can ask a question then.
Thanks so much. So I'm asking my question. So I wonder about the angular momentum loss mechanism, because your magnetic white dwarf, your massive white dwarf like the moon, is rotating much subcritical. So like the majority of the angular momentum was lost. So I was imagining the total mass before, let's say in the merger scenario, the total mass before the merger may not be much more than 1.4 or 1.5. Otherwise, they would explode in the type 1A. So the total mass lost during, before after the merger till now, the total mass lost is less than 10% of the total mass of the current mass.
That's what Josiah's models showed. There isn't that much mass loss in that phase.
Yeah. So why 10% of a mass loss carried away nearly 100% of the angular momentum?
Yeah, you'll have to ask Josiah or like read the paper. I'm not 100% sure. I guess the winds are very strong when they're very fast in that phase of the red giant phase, and that's how a lot of angular momentum is lost. But that's just the calculation that is done. It finds that very, very little mass is lost, but that little mass carries a lot of angular momentum. I don't really remember. I
think it's so it should be due to magnetic braking, right?
There's no magnetic fields.
No, I think it's just that the envelope is very low mass, right? It's a very extended envelope.
Very big. It's 100
10 to the 5 times the radius of the white dwarf, but only a few % of the mass.
Yeah.
I see.
So if you assume it's rigidly rotating, I mean, I think there is an assumption that it's not a huge differential rotation, but even as long as it's close to rigid, I think that's just why you don't need any extra braking except to keep the envelope co-rotating.
Oh, I see. So it's the core envelope structure, right? That is yeah. So you only need to lose a tiny fraction of the mass, which is at very large distances. I see.
Yes.
Thanks.
Okay.